going to talk about sort of why I love recursion and why I love, in particular, I love top-down recursion. So I'll give a few reasons. Um, First, recursion typically minimizes the lines. It minimizes the number of lines of code, and this is super valuable, especially in a coding interview, because you want to minimize your mistakes. You have time constraints, and yeah, like you basically want to like minimize the number of mistakes and the amount of time it takes for you to get to the right answer. So as a result, like if you can have fewer lines, it's super valuable. It's also why I love Python, because it's because you don't have to specify types. You're like cutting down the amount of like characters you're writing by at least 50%. So if you can't interview in Python, just interview in Python or interview in a duck type language. Okay, cool. All right, two. Um, Typically, if you can use recursion, it's very valuable because you can. This goes back to sort of one. The code, it can be very clean because you're sort of just building on top of what you've already done. Um, uh, because you're sort of building case by case by case, and each case is just building on the previous case. And the solutions are very, very clean. Okay, and then number three is, and this one might be surprising to some of you, the perf can be easily optimized. So I'm going to talk about this last one the most because I think a lot of people don't typically do this, but basically in almost all cases when you can do DP, you can do it using top-down recursion and then using memoization. And your big O per perf will be similar to DP. It's not even similar. It's like equivalent in big O notation. It's equivalent asymptotically, in other words. Okay, so let's walk through like a very simple example. So I'm sure you've seen like fibonacci n, where like if n less than equal to equal in 0, 1, return 1. If else, return fib, n minus 1 plus fib n minus 2. All right, cool. And we all know that this is like on squared, or sorry, o2 to the n. So I'll just write that because I misspoke. Basically, your recursion tree will call, if you think about your recursive calls as a tree, fib n calls fib n minus 1 and fib n minus 2. And so it calls, it has two leaf nodes, and then each of those leaf nodes, like fib n minus 1, has two other leaf nodes, fib n minus 2, minus 1 minus 1, fib n minus 1 minus 2, or fib n minus 2, fib n minus 3, so forth and so on. Okay, cool. So that's not awesome, but actually it's very easy to memoize this. And I think if more people just solve problems with recursion and then just memoize it, they would have fewer lines of code. Their code would be very clean, and their big O perf would basically be optimized. So the memoization is actually incredibly simple. You just put in a dictionary, all right? So here I put in a dictionary memo, and then all I do is if memo.get n, return memo n. Okay. Otherwise, like we need to set memo n equal the previous result. So let's say result equal this, and then we return the result. Okay, this is like literally I just do this, like I'll basically whenever somebody asks me about like the big O, I'll just be like, okay, I'm memoizing, and I literally just go through, create my dictionary, and look at each of my return statements, and I set the memo, and then I put this if this check. I check for a memoize result and return it otherwise, and then on all the return statements I just set the memoization, or like I memoize the result. Okay, and this has order. This new algorithm is ON. Okay, and the reason why is you know, you can imagine you go down your this Fibonacci is call is basically uh, it'll do depth first search. It's basically it'll do depth first search, so it'll go, the first call will be fibn, then fibn -1, then fibn -2, then fibn -3, and so forth and so on. And as it calls back, it'll start returning memoized results. So we can actually, there's a pretty easy way for me to demo this. Let me, okay. So I'm going to comment out the part where I actually use the memoization, and then let's just, I'm going to print like the actual calls. Yeah, let's do that. So every time I call Fibonacci, whenever I make a call, or recursive or otherwise, I will print the call. So let's go through here, and then we go here. And as you can see, there's like a lot of lines of code, or there's like many calls. Okay, geez, that's a lot. So it's like 1, 2, 3, 4, 5. Okay, I'll also do a count. I equals 0, I plus equal 1, and then print I. So how many times does it get called recursively? Oops. What does it say? Local variable I, reference before assignment. Wait a minute. Reference before assignment. That's not right. I equal I plus 1. That seems a little bit odd. Let's try that again. Alright, so as you can see, it got called like 177 times. That's on the order of 2 to the n. That's like around 2 to the 7th, I believe. Yeah, it's like around 2 to the 7th. I think 2 to the 7th is 128. So it's around 2 to the 7th, 2 to the 8th. Okay, now let's see what happens if we memoize. And this time we print again, fib. Oops. We print it at the top yet again. And we will, oops. Oops. Gotta do that global I, man. Okay. And yeah, you see that we have 19 calls to Fibonacci. Yeah, so I really strongly advise using recursion if possible. Again, the code is super clean, it minimizes the lines of code, and the perf is asymptotically similar to a DP solution or an iterative solution. Yeah, that's it. Cool.